Hello and welcome to the AI Affairs podcast. We are doing a deep dive today into, well, one of the biggest transitions happening in tech right now.
It really is.
I'm talking about humanoid robots. They're moving from these, exciting but kind of fragile prototypes into real, actual industrial assets.
Yeah, embodied AI is finally leaving the lab, it's hitting the factory floor, and there are billions in investment behind it.
Exactly. So our mission today is to unpack the surprising success metrics from these first deployments, and then we have to contrast that with the other side of the coin.
The cybersecurity risks.
Which are immediate,
Mm-hmm.
they are severe, and they're buried deep inside the architecture of these machines.
That's right. So for you, the listener, think of this deep dive in two halves. First, we're going to set a baseline. We'll look at a major automotive pilot project, see what these things can actually do.
And then?
Then we pivot. We go straight to the security side. We've got empirical data from a teardown, and we're going to show exactly how a software bug can translate into, well, immediate physical danger.
Because these things are big and they're powerful.
Powerful, fast, and very capable of causing harm if they're compromised.
Okay, let's start with the hard numbers then. The big story here is the BMW Group's pilot program with the Figure 02 humanoid robot.
Right, at their Spartanburg factory in South Carolina, a massive facility.
So what was so special about this test? What were they trying to solve?
Well, it's fascinating because this wasn't just some showpiece task. They were solving a real manufacturing bottleneck. The Figure 02's job was to insert sheet metal parts into fixtures.
The ones used to assemble the car's chassis.
Exactly. And that task is, it's hazardous, it's repetitive. It's exactly the kind of job that's ergonomically stressful for a person to do all day.
Inserting parts, though. It doesn't sound revolutionary on its face, but I guess the point is that a general-purpose robot is doing it. How precise did it need to be?
That's the key. It requires advanced dexterity. We're talking millimeter-level accuracy in a dynamic factory environment. And we actually have the data from their 11-month deployment.
11 months. So this wasn't just a weekend trial.
Oh, no. This robot ran 10-hour shifts, Monday through Friday. It was basically operating just like a human associate, and it directly contributed to producing the X3.
Give me the numbers. What did nearly a year of factory work actually look like?
Okay, so over that period, the robot loaded more than 90,000 parts.
90,000.
Its total runtime was over 1,250 hours, and that works out to something like 200 miles of physical steps on the factory floor.
And all that work helped build 30,000 vehicles.
Over 30,000 X3s, yes.
That's undeniably substantial. But let me just push back on that for a second. 90,000 parts. Is that really a game changer? Or is it just, a little better than a custom industrial arm that costs a fraction of the price?
That is absolutely the right question to be asking. And the value isn't just in the raw number. It's about the flexibility and the really demanding targets they hit.
The KPIs.
Right. The KPIs were all about speed and precision from a general-purpose platform. The total cycle time had to be 84 seconds. And the actual loading part, just 37 seconds.
And the accuracy.
That's the critical part. Placement accuracy had to be over 99% successful per shift. And often, that meant placing a part within a strict 5mm tolerance.
In just a couple of seconds.
In 2 seconds. So the point isn't that it replaced the cheapest machine. The point is they proved a bipedal robot could hit machine tool level precision reliably in a high-speed environment.
So the hardware really passed the stress test. But even with all that success, they're retiring the Figure 02 for the Figure 03. What was the big takeaway? What broke?
They learned exactly what fails under that kind of constant stress, high heat, high vibration. The engineers found that the #1 hardware failure point was the robot's forearm.
The forearm. Interesting.
Yeah, think of it like packing a supercar engine. The electronics that distribute signals to the wrist were jammed right up against thermal vents.
So they were overheating.
Constantly. It was a classic engineering compromise, driven by the need to make everything as compact as possible.
So it wasn't the motor itself failing, but the little distribution board next to a heat source.
Precisely. So for the Figure 03, they've completely re-architected it. They got rid of that problematic board. Now each wrist motor controller talks directly to the main computer.
Which simplifies things.
A lot. It reduces complexity, helps with the thermal management, and boosts reliability. And that's a lesson they only learned from those 12,250 hours on the line.
And BMW is definitely not alone here.
No, not at all. You see, GM working with Thematic, Mercedes-Benz is testing Apptronic's Apollo robot, and of course Tesla is talking about thousands of Optimus bots in their own factories by the end of next year.
Okay, let's zoom out a bit. Let's look at the bigger picture.
Yeah.
Beyond just BMW, How mature is this industry globally? Who's really pushing this forward?
Well, in terms of just sheer geographical dominance, China has a significant lead.
In what way?
A review of the companies in this space shows China accounts for about 39% of them. The U.S. is next, at 24%.
That's interesting. If China has the lead in the number of companies, why are all the big high-profile deployments we hear about, like BMW coming out of the U.S. and Germany?
That is a key distinction. A lot of the U.S. and European focus is on the final, highly integrated product, a robot like Figure O2 that's ready for immediate industrial use.
And the Chinese presence is, what, more focused on components?
It could be. China's lead might reflect a broader base of suppliers, R&D, component makers, but the critical commercial deployments that are setting the performance standards right now, they're mostly centered in the West.
And speaking of standards, despite the BMW success story, you still hear a lot that these robots just aren't ready for prime time. What's this readiness gap about?
To understand that, we have to look at two different metrics. There's production readiness level, or PRL.
Okay, so can the robot actually do the job?
Exactly, the hardware maturity. Then there's commercial readiness level, KRL.
Which is, can you actually sell it and deploy it at scale, safely, legally?
That's the problem. The hardware, the PRL, is getting pretty high, level 6 or more for the top models. But the commercial readiness, the KRL, is lagging way behind, maybe at a 4 or 5.
So the robot can do the task, but the whole ecosystem around it, insurance, regulations, liability, can't handle it yet.
That's the bottleneck. The KRL challenges are huge. You need accepted safety standards, you need certifications that work everywhere, you need scalable training programs, and maybe the hardest part, you need to get insurance companies on board.
And you need industry to just accept them. Which brings up another point. We saw that data from Fraunhofer IPA, where a majority of experts are questioning the whole design.
Bipedalism, yeah.
60% of them doubt that 2 legs are even necessary for most factory jobs, like moving boxes.
And that's a crucial question for the future of investment here. Many experts argue that a wheeled platform, or even just a stationary robot with 2 arms, is way more practical for now.
It's just more expedient.
It is. Why introduce all the complexity of dynamic balance if you can just roll from point A to point B?
So if 60% of your own experts are skeptical, why are companies like Figure and Tesla spending billions on 2-legged robots? Is this just a moonshot bet?
It absolutely is a bet on the future. The thinking is that once these robots achieve true general-purpose dexterity, climbing stairs, using human tools, navigating messy spaces, their versatility will just eclipse a simple wheeled system.
But that's a long way off.
It is, and it creates this huge uncertainty. When you look at long-term sales projections, the range is massive. Some say 2 million units a year by 2050, others say 50 million. It all depends on whether the bipedal design actually proves itself commercially.
Okay, so we've established the hardware works, that's PRL, but the market isn't ready for the KRL. Let's pivot now to the immediate danger this creates. What happens when you put commercially immature tech into a high-stakes environment? Let's talk about the Achilles heel, cybersecurity.
This is, I think, the most serious issue facing the industry. It's what we call physical cyber convergence.
Meaning, a software problem becomes a real-world problem.
Exactly. We're not talking about a server crashing. We're talking about a software vulnerability that makes a 200-pound machine do something it's not supposed to do. If a robot working next to a person is compromised, what happens? Does it drop a heavy part? Does it lurch sideways and trip someone?
So what does the evidence show? We had the teardown analysis of the Unitree G1 robot as an example.
We do, and the physical assessment alone shows multiple vulnerabilities. Even with a sealed exterior, there's a primary access point in the chest cavity, right to the main control board.
Which opens it up to hardware attacks.
If you can get past physical security, yes. And inside, the complexity is, well, it's alarming. The robot runs 22 interconnected services for things like motion, state awareness, communication.
And how are all these services talking to each other?
Through middleware. And critically, it's an old implementation of ROS2 Foxy.
And for anyone listening who isn't a roboticist, what does old mean here?
It means it reached its end of life in May 2023. Any security flaws found after that date are not being patched. You're essentially operating a giant, unpatched, walking vulnerability.
What about physical access to the hardware itself?
The main computer, the ROC chip SO, is exposed. And even more concerning, there are modular JST connectors everywhere inside.
What are those?
Think of them as cheap, simple internal USB ports. They make maintenance easy, but they are also perfect insertion points for malicious hardware if anyone gets inside.
Wow. Okay, so beyond physical access, what about data?
Right.
If you put one of these in a sensitive factory or a hospital, could it become a Trojan horse?
The risk of covert surveillance is massive, and the evidence is damning. The analysis showed these persistent TCP sessions connecting to external servers
Just phoning home.
constantly. And here's the core failure. The team was able to capture plaintext telemetry payload before they were encrypted. The robot was broadcasting comprehensive data completely in the clear.
What kind of data are we talking about?
Everything. All the battery cell voltages, continuous IMU data pitch, roll, yaw, the exact position of all 20-plus joint motors, CPU usage, everything you would need to build a perfect digital twin of that robot's actions.
So an attacker could learn the entire workflow of a factory floor just by listening in.
They could learn the flow of materials, learn when people take breaks, and then use that knowledge for targeted sabotage or espionage later on. It's a huge risk.
That's passive surveillance. Did they find a way for an attacker to actually take control?
Yes, and this is probably the most alarming finding. The robot uses a proprietary encryption system called Mixer to protect its configuration files.
And it wasn't very good, I take it.
It had a fatal flaw. One layer used blow-fair encryption, but it relied on a 128-bit static key.
Static meaning it doesn't change.
It doesn't change, and worse, it was the exact same key on every single G1 robot they manufactured.
Wait, are you serious?
Yeah.
The same key for the entire fleet.
Identical. It's like every bank in the world using 1, 2, 3, 4 for their vault combination. This flaw meant the key could be cracked in less than 0.02 of a second.
And once you have the key,
You can decrypt the configuration files on any G1 robot, modify its behavior, change its safety limits. You can command it to do anything.
that one finding just undermines the entire commercial viability of that fleet.
Yeah.
So if we can't trust proprietary security, what's the path forward? How do we manage this risk?
The solution is to get away from this security through obscurity mindset. We need comprehensive, dynamic security assessment methods, something like Sesame.
And what is Sesame?
It stands for Automated Security Assessment of, well, of modern multi-robot systems.
Yeah.
It's a framework that creates a standardized, verifiable process for finding these vulnerabilities.
How does it work?
It takes known vulnerabilities, things like CVEs, and maps them directly to known attack patterns, or CAPEX. And from that, it builds these detailed visual maps called template attack trees.
So it visualizes the entire attack chain, from one small software bug all the way to a catastrophic physical event.
Precisely. It lets you see the whole multi-stage attack before it happens, and this isn't theoretical. It's been used to detect and stop a GPS spoofing attack on a drone fleet. It's identified flaws that could let someone just stop a healthcare robot in a hospital with a simple unauthorized command.
I see. So it connects the cyber risk to the physical outcome.
Which is what's desperately needed to bridge that commercial readiness gap, that KRL we talked about.
Okay, let's wrap this up. Let's
Yeah.
summarize what we've uncovered in this deep dive. On one hand, we've seen humanoid robotics achieve real, tangible industrial success.
Right, the BMW pilot proved it. 90,000 parts loaded. The endurance is there.
But that success is still commercially fragile. The KRL, the commercial readiness level, is lagging way behind the hardware, and the industry itself is still debating the whole bipedal design.
And then, most critically, just beneath that sophisticated hardware, we found these massive immediate security holes.
Manufacturers shipping robots with fatally flawed security, static encryption keys for an entire fleet, and just pervasive, unencrypted data leakage.
The bottom line is, as we integrate these robots into our critical infrastructure factories, healthcare, you name it, security can't be an afterthought. These proprietary, easily broken systems have to go.
And be replaced by robust frameworks like Sesame.
They have to. It's the only way to manage this dangerous nexus between a cyber failure and a physical risk.
So here's a final provocative thought for you to take away. Think about what an advanced humanoid robot really is. It's highly dexterous, it's physically strong, it's often connected to the network with insecure links, and it might be running outdated software. The real threat isn't just a random accident. It's a compromised system that's acting as an industrial Trojan horse, quietly stealing your most sensitive data while at the same time waiting for the command to cause physical harm to itself or to the people working right next to it. Thank you for listening, and see you next time on AI Affairs.